The universe, vast and mysterious, filled with enigmas that challenge our understanding of physics. Among the most perplexing is the information paradox, tied closely to the enigmatic nature of black holes. The information paradox first came into the spotlight in the 1970s thanks to physicist Stephen Hawking. It emerges from a clash between quantum mechanics and general relativity. To grasp it, we need to explore black holes and quantum theory. Black holes are cosmic regions where gravity is so intense that nothing, not even light, can escape. According to general relativity, a black hole is defined by its event horizon, the boundary beyond which escape becomes impossible. But here's where quantum mechanics throws a curveball. In 1974, Hawking proposed that black holes emit radiation due to quantum effects near the event horizon. This radiation, now known as Hawking radiation, results from particle-antiparticle pairs that spontaneously appear near the event horizon. One particle falls into the black hole while the other escapes, causing the black hole to lose a tiny bit of mass. Here lies the paradox. If black holes emit radiation and lose mass, they should eventually evaporate entirely. What happens to the information about the matter that fell into the black hole? Quantum mechanics insists that information must be preserved, yet the complete evaporation of a black hole suggests this information could be lost forever. This conundrum, known as the information paradox, sits at the heart of our dilemma. They suggest that our theories, quantum mechanics and general relativity, might be incomplete or need modification when applied to black holes. One controversial resolution is the firewall hypothesis. It suggests a firewall of high-energy particles forms at the event horizon, destroying any information that tries to pass through. This idea, however, contradicts general relativity's principle that the event horizon should be a smooth, benign region. Another intriguing approach involves the holographic principle. This principle posits that all information in a volume of space can be represented as a theory on the boundary of that space. The ADS-CFT correspondence suggests that the physics inside a region, like a black hole, can be described by a lower dimensional theory on its boundary, implying that information is encoded on the event horizon's surface. Black hole complementarity adds another layer, suggesting that information is both reflected at the event horizon and passes through it. To an outside observer, information never falls in, while to an infalling observer it passes through without encountering any firewalls. Recent advancements in theoretical physics bring new insights. Research into entanglement entropy and quantum information theory introduces concepts like quantum extremal surfaces, suggesting that information might be preserved in a highly scrambled form within the radiation. The idea of scrambling posits that information, while seemingly lost, is actually dispersed in such a complex manner that it becomes nearly impossible to retrieve. Studies on the dynamics of quantum information in systems like black holes indicate that Hawking radiation might encode information in a highly entangled state. Finally, the concept of soft hair proposes that black holes possess low-energy quantum excitations that could store information about what falls into them. This ties into the idea of black hole microstates, suggesting each black hole state is unique and corresponds to a particular configuration of quantum information. The information paradox continues to challenge and inspire physicists, pushing the boundaries of our understanding of the universe. In the realm of quantum mechanics, the preservation of information is a cornerstone principle that maintains the coherence and predictability of the universe. But why is it that information cannot be destroyed? Unitarity of quantum mechanics. At the heart of quantum mechanics lies the principle of unitarity. Unitarity ensures that the evolution of quantum systems is governed by reversible transformations, preserving the total probability of all possible outcomes. This means that every quantum event can, in principle, be traced back to its origins without losing any information. No-cloning theorem. The no-cloning theorem plays a pivotal role in the preservation of information. It asserts that it is impossible to create an exact replica of an unknown quantum state. This intrinsic property of quantum mechanics prevents the duplication or destruction of quantum information, ensuring its fidelity. Conservation laws information, much like energy and momentum, is conserved in the universe. This conservation is a direct consequence of the symmetries inherent in physical laws. Just as energy cannot be created or destroyed, information too adheres to this fundamental principle, maintaining the balance of the cosmos. Black hole information paradox. The black hole information paradox brings this principle into sharp focus. Stephen Hawking's discovery of Hawking radiation suggested that black holes could evaporate, seemingly erasing the information about what fell into them. However, if information were truly lost, it would violate the principles of quantum mechanics. This paradox underscores the necessity for information preservation even in the most extreme conditions. Quantum entanglement provides a mechanism for the preservation of information. When particles become entangled, their states are interconnected regardless of the distance between them. This entanglement ensures that information is not lost but rather distributed across the quantum system, allowing for its eventual recovery. Holographic principle and ADS-CFT correspondence. The holographic principle and the ADS-CFT correspondence offer a profound perspective on information preservation. These theories propose that all the information within a volume of space can be encoded on its boundary. This implies that the universe's total information content is conserved, even if it appears hidden or dispersed. Conservation of entanglement entropy. Finally, the conservation of entanglement entropy highlights the intricate dance of information within quantum systems. Entanglement entropy captures the hidden correlations between different parts of a quantum state. Under unitary evolution, this entropy remains conserved, ensuring that no information is ever truly lost. The preservation of information is not just a theoretical construct, but a fundamental aspect of our universe's fabric. The information paradox, which revolves around the apparent loss of information in black holes due to Hawking radiation, has not been definitively solved yet. However, several proposed solutions and insights have emerged over the years, suggesting potential resolutions to this long-standing puzzle. Here are some of the key ideas that have been put forward. Black hole complementarity. Black hole complementarity is a proposed solution that suggests there are two different complementary descriptions of the physics near a black hole. One from the perspective of an observer falling into the black hole, infalling observer, and one from the perspective of an observer outside the black hole, external observer. Infalling observer perspective. According to this perspective, the infalling observer encounters no unusual behavior at the event horizon or inside the black hole. The observer freely crosses the event horizon and reaches the singularity without noticing any firewall or loss of information. External observer perspective. From the external observer's point of view, Hawking radiation carries away information about what fell into the black hole. The radiation eventually leads to the complete evaporation of the black hole. Black hole complementarity posits that these two descriptions are not contradictory but complementary. Information is preserved in a global sense, from the external observer's viewpoint, but locally, from the infalling observer's viewpoint, it appears as though information is lost. Holographic principle and ADS-CFT correspondence. The holographic principle suggests that all the information inside a region of space can be encoded on its boundary. The ADS-CFT anti-de Sitter conformal field theory correspondence provides a specific realization of this principle, suggesting that a theory of quantum gravity in a higher dimensional space, like a black hole, can be equivalent to a lower dimensional quantum field theory defined on its boundary. This approach implies that the information inside a black hole could be encoded on the event horizon's surface, thus avoiding the paradoxical loss of information. 3. Firewall hypothesis. The firewall hypothesis proposes that there is a high-energy firewall just inside the event horizon of a black hole. This firewall would destroy any information carried by infalling matter, thereby resolving the paradox by sacrificing the smoothness of the event horizon. However, this hypothesis is controversial because it conflicts with general relativity and the idea that nothing dramatic should happen at the event horizon. Soft hair. Hypothesis and black hole microstates. Recent work has suggested that black holes may possess soft hair, which are low-energy quantum excitations that can encode information about what falls into the black hole. This concept is related to the idea of black hole microstates, which suggest that each black hole state is unique and corresponds to a particular configuration of quantum information. These microstates might preserve the information in a scrambled or highly encoded form, allowing it to be recovered in the Hawking radiation. Quantum information theory. And scrambling advancements in quantum information theory have provided insights into how information can be encoded in highly scrambled forms. The process of quantum scrambling indicates that information might be dispersed in such a complex manner that it is effectively lost in a local sense but can be recovered in a global sense. While the information paradox remains an open question in theoretical physics, these ideas bring us closer to understanding how information might be preserved in the universe's most enigmatic phenomena.